So today's lesson is about logarithmic functions. We know that the basic exponential function y is equal to b to the x is what we call one-to-one. And since it is one-to-one, we can say, so basically this thing actually has an inverse. All right, so let's go and do that. So for the inverse, what we have to do is we have to go and interchange x and y. So remember, our original equation was this: y is equal to b to the x, right? So now we're going to have to write it as the following: x is equal to b to the y. All right? So in math, we can isolate it by using a different function. We isolate for y using a different function called the log. And you write it as this: y is equal to the logarithm of x base b. Or you could say it as the log of base b that produces x. So essentially what we're doing is we're finding the y value. We're finding the x. We have the x value. You need to know what the y value is. That gives you that original final answer. Okay? Here's what you really need to note based on all of this. Note the log is really an exponent. Very similar to what we have studied all our lives in mathematics, and now we are finishing it off with something that undoes it. All right, so let's go and talk about how we show that the log is nothing more than an exponential. Okay, so here's what we're going to do. We're going to come up with a series of logarithmic equations, and then you will see how they represent the exponential form. So imagine we have these basic logarithms, okay? All right, so we have these basic logarithm forms. I'm going to go and add a few more because I think we need to really focus on this. So we're going to have the log of base 10 of 1 over 1,000 and log of base b equals 0. All right, so here is our logarithmic form table, and we're going to come up with the exponential representation of what we see. So for this first one, it says the log of 16 is equal to 2. What it's actually saying is, well, 4 raised to the exponent 2 is equal to 16. For this next one, you'll notice we have the log of 16. So the log of base 16 is 2, and the answer is 1/4. So what's that saying is, for the number 2, for the base of 16, if we raise it to the 1/4, we get 2 back. For the next one, if I have log base b gives b is equal to 1, that means b to the exponent 1 is equal to b. For the next one, we have log base 10 of 100 is equal to, I'll tell you what that is. That's -3. So basically what you're going to do is you're going to say 10 to the -3 is equal to 1 over 1,000. So for this last one, we have b to the exponent 0 is equal to 1. So let's go back to the 16 problem, right? For the 16, the 4 represented the base of our problem. The 16 represented the result. And finally, this 2 represented the exponent that was attached to its base. All right, so now let's talk about the graphs of y is equal to b to the x and y is equal to log base b of x. All right, so let's move on. So here are the graphs of what these things looks like. So if I drew a basic graph like so, right? I showed you that the exponential looks like this, right? And this was y is equal to b raised to the x. So when I want the logarithm of that, right? When I want y is equal to the log base b of x, we have an interchange of x and y to get this. So that means we essentially swap our x's and y's. So essentially, our graph looks like this, and there is a reflection in y is equal to x. So essentially, our graph looks like this. Now, here is the cool part. I know that this intercept is 0, 1. So I could write 0, 1 for here. Now, when I look at the inverse, i.e. the log of y b to the x, you've got this, 1, 0. So all we've done is just interchange all of the values for this. Now, this graph is for when b is greater than 1. All right, so now here's the question. What would happen if b was, say, less than 1? Let's see what that looks like. So if I'm actually considering this, you would have your graph looking like this, okay? And for our graph of y is equal to b to the x, where b is less than 1 but greater than 0, which is a fraction, okay? Then when we find our log, remember it gets reflected in y is equal to x, which means that this is still 0, 1 here, but our point is reflected about by the x-axis, so we get 1, 0, and our graph now looks like this. And now it looks like this. Comes through, crosses the x, the y equals x, and then comes out this way. So our graph is y is equal to log base b of x. And remember, our b value was less than 1 but greater than 0. Okay? So now we'll talk about the properties of the logarithm. Here's what you need to remember, right? The domain of this thing is always greater is x greater than 0. And remember, this is our basic equation. Y is equal to the log base b of x, and its range is all of the y-axis, right? The x-intercept is always 1, 0. And if b is greater than 1, we always know that this thing is actually increasing. All right, if it's between 0 and 1, it's decreasing. It always has a vertical asymptote on as x equals 0, and that is our vertical asymptote. The equation is y is equal to log, and it's always continuous. And remember, it's also 1 to 1, so that means if I know what my equation is for y is equal to log b to the x, I can always go and find its equivalence. Okay? As an inverse. So now we're going to talk about the laws of logarithms. So when we talk about the laws of logarithms, we need to address the multiplication and what that means, and then the division and what that means. So if I have the log of base b, where I have two numbers, m and n, multiplied as the result, that means we have the log of b m plus the log of b n. All right, now here's 2. Let's say I have division. So we've got log of b of m divided by n. You're going to have the log base b of m minus the log of base b n. All right, now the reason why that is because of a thing called exponents. When we divide exponents, we take the top exponent and divide and subtract. We take the top and subtract from the bottom, and that's where we get this, the subtraction. When we have two exponents multiplied by each other, all we're going to do is just add them. Okay, so now imagine if I have an exponent that looks like this, a logarithm that looks like this. The log base b of m to the exponent c. All right, so what you do is you literally just bring it down and you say c is equal to log base b of m. So now let's go and look at part 4. So the fourth part of this says that if I have the following, the log base b of m of n is equal to the log of a n divided by the log of a to the b, and we're done. That's it. We'll go over these examples to come up with solutions, okay? All right, so we're going to determine the exact value. Let's say I have this, the ln. Let's write this. I'm going to write this in script. So if I have the ln of the following, e to the 4 times e to the 9. Here is a note that you need to recall. The ln of x is equal to the log base e of x. So we're just using a short form to cut down on the amount of writing that we're using for these logs, right? So if I have the ln of 13, what I write is the ln of e to the 13, because remember, using our exponent rules, we actually pull together 4 and 9 to give 13. But now, for this, when we have an exponent on here, all we end up having to do is bring it down to the front of this bracket, and we end up with 13 ln of e. Now, here's another note. If you ever see the ln of e, that's just equal to 1. So we end up with 13 times 1, which is just 13. So now let's take a look at our next problem. And our next problem involves something raised to the log of something else. So let's say I have e, let's go, this is a question B. So you write 25 log of 5 base 8. All right, here is our solution for this problem. So the first thing that you have to identify is the fact that this is a base 5. So we're going to change the exponent to base 5. So 25 turns into 5 squared. So we end up with this 5 squared raised to the log of 5, 8. All right, so now this turns into, ready? This is now literally a power of a power. So now we have the following: 5 raised to the 2 times the log of 5 base 8. Now, here is something that I need you to recall. I told you that the log of 5 base 8 is actually saying, okay, what exponent, if you think about it, I need to know what exponent with base 5 gives 8. So that actually is, so when we're using that here, that actually is the basic exponent. So you know what we should do? We should go and say, all right, forget this. Let's just go and take this information, take this 2, and stick it onto the 8. So remember, I said that something that was raised to the 2 could be stuck on the 8. So you end up with 5 log 5 raised to the 8 squared. There you go. So now, with our problem, you'll notice something weird happening. We can actually take all this information now, and we're going to use it to our advantage. So now what you're going to have is this. So now you have 5 raised to something base 5, which is 8 squared. So you know all that does is it actually just drops what our answer is. So we end up with just 8 squared. So just think about it. This says, give me the exponent that gives me 8 squared with base 5. So that's the exponent, and I have base 5 here. So all I end up with is 8 squared, which gives us a final answer of 64. Now just make sure that you put your answers in a box so that I can clearly see them. So imagine I give you a problem like this. Find a logarithmic function that goes through 4, 1/3, and the logarithmic function is f of x is equal to log base b of x. So now when we substitute, we literally just do this. F of 4 is equal to log. We don't know what the b value is, but we do know what the x value is. The x value just happens to be 4. Now, f at 4 is actually 1/3. So we're saying log base b of 4. So what that actually means is that we have b to the 1/3 is equal to 4. So just remember that when we talk about this, we're saying what exponent with base b gives the final answer of 4. So now when we solve for b, we end up with b is equal to, well, 4 cubed, which means that b is equal to 64, and that is our answer. So as our final solution, we can say the following. All right? We can say, therefore, f at x is equal to the log of 64x. And we're done. All right, so imagine that I ask you to determine the following, right? You need to figure out what the domain, the x-intercepts, and the vertical asymptotes for this function, 1 minus the log of 4 of x minus 4 is. All right, so here is how we check that. So remember when we were finding our domains, right? The domain was always calculated by finding the values where you had something weird happening. So for the domain, here's what we're going to do. We have to look at this portion of the graph. Because if you end up putting a negative portion for this bracketed thing in here, the log is impossible. It does not work. So we have to go and calculate this. We have to say, well, x minus 4 has to be greater than 0. So we end up with x being bigger than 4 as our answer. So that means we say the domain is equal to the set of x being 4 going all the way to infinity. Okay? And there we have it. And so now we've calculated our intercepts. So let's go and take a look to see what our intercepts are. Okay, so now for our intercepts. When you think about it, when we want the y-intercept, we want to let x equal 0. So when you do that, you're going to see the following. You're going to get y is equal to 1 minus 2 log base 4 of negative 4. Now, this situation is impossible. Okay, so we can't have, in this case, no y-intercept. So we cannot have a negative value for the final answer for this portion of our graph. So we have to say this is therefore no y-intercepts. Now, what about the x-intercepts? The x-intercept we have to let y equal 0. So what that means is we have 0 is equal to 1 minus 2 log of 4 of x minus 4. So now all we have to do is we have to take this whole thing here and move it to the other side of this equation. So now we have 2 log 4 of x minus 4 is equal to 1. And now to get the log by itself, what we'll do is we'll divide both sides by 2, which means we have the following answer. We have 1/2 equaling log base 4 of x minus 4. So what that means is we have 4 to the 1/2 is equal to x minus 4. So 4 to the 1/2 is just 2, which is equal to x minus 4. And when we continue solving, we end up with our final answer of x is equal to 6. So that means our x-intercept is 6, 0. So now we also have to calculate the y-intercept. So let's go and do that. All right. So now for the y-intercept, sorry, not the y-intercept, the vertical asymptote. For the vertical asymptote, this is what our equation looks like. Y is equal to 1 minus 2 log of x minus 4. Now, all we have to do is focus on what the log is actually doing. And this whole part here cannot equal 0. So all we have to do is we say, okay, x minus 4 can't equal 0, so we end up with x cannot equal 4. So that means our vertical asymptote is x is equal to 4. Now, if we went and graphed this, let's look at the overall picture of what we have here. So I'm just going to zoom back out and look at all the information that we have. So right now we have the domain is x being bigger than 4. So if I graph this, the first thing that you're going to do is you're going to find x is 4. And then you're going to draw a vertical asymptote. And you're going to identify that as x is equal to 4. Now, since I have my vertical asymptote, I wanted to find out if there was a y-asymptote. A y-intercept. We found that there isn't a y-intercept, right, based on what we calculated, but we did find the x-intercept being 6, 0. So 6, 0 is somewhere over here. So I'm going to put that as red and put the point 6, 0 on my graph. Now, using some additional points like these points of 6, 0, 5, 1, and 8, -1, you just plug the x values in. You end up with your graph looking something similar to this. And we're done. And don't be shy to use those extra points because they do help you out. They help you figure out how the graph is going to look. So for homework, I want you to do page 303, number 1 to 31 odd.